approaches infinity. It's shooting towards the sky, which is what? As x goes towards infinity, where's this thing going? To positive infinity. So that's why doing a graph, you can really see where the answer is. Hey, I'm going to get another point. What's the number less than negative 1? Negative 2. That's 4 over negative 2 plus 1. Negative 4. Which puts it 1, 2, 3. And when that's down in here. See that little triangle there? And when it's right in this triangle. We didn't need it for our answer, but I did want to point out this graph does exist over here. Does this? Let's see, like that. That's what we wanted. And let me put it down. What's the limit? As x approaches infinity of x squared over x plus 1. Oh my gosh, it's going to what? Positive infinity. Now I want to talk about this. I said you don't have to find the slant aspect to find these answers, right? So can we make this one easy? You don't want to make a slant asymptote? Here's the deal. If you get this scenario of highest power on the top for rational functions, I want you to ignore this one here and I just want to divide that. And I want you to think the end behavior of that function. What's x squared over x? So I'm going to write that down. Y equals x. And when this is called the end behavior, of this expression, if I divide, you see that big? I'm just thinking, that'd be y equals x, right? Do you know about that behavior? If you know the end behavior of that, you know the answer to this question. How does that graph behave? It does what? Y equals x goes like that. So where's it going? As x goes this, that's what I mean. So you only have to do that. You can just go in there, take this, reduce it, and think about that expression as x goes to infinity, the end behavior of that expression. Isn't that cool? And it works. So I wanted to give you a few more that you can do, so you can sit there and go, all right, let me see if I can just find the end behavior of that.
What if it was like x cubed or something?
I like it. Yeah, x cubed over x. Now that makes that x squared brilliant. He goes, but now you got a parabola, but guess where it's still going?
Yeah, it's still like that.
Exactly. So I love that how you knew that. You go, wait, you're going to get an x squared now, but you knew to look at the end behavior. And there it goes towards infinity. Isn't that cool? So absolutely, you do not have to go through this. If you're just like, I don't want to do this. No. Look at, for this scenario here, higher power on the top for a rational function. Look at the end behavior of that expression. Okay? All right. This is just a Horace. This is just a Horace 0, right? Yeah, you're like, got it. I think we got this stuff. Okay. Pretty cool. Well then, let me throw 3 at you and see how you do. See if you can get 3 for 3. 3 for 3. Oh, is that okay? I'm racing?
Yeah, cool.
Nice. Nice. Yeah, this thing's got slant asymptotes. Get it out of the way. Hey Joe, I have one more. Real quick. What about that? Anybody know that end behavior? What is that equation? If you reduce that.
Negative.
Y equals negative x. And how does y equal to negative x behave? What's the end behavior of that graph? Joe got it. He says it's going to negative infinity. So what would be the limit as x approaches infinity? Negative infinity. Does everyone see that? True? So I'll write down the limit. As x goes to infinity of a negative x squared over x plus 1. Well then, it's got to be behaved just like this to find the actual limit. Negative infinity. Hey, can you do this numerically? Remember, there's 2 ways to find limits. Algebraically, numerically, and graphically. I mean, can you find that numerically? Yeah, just start plugging in what? Really, 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 really big numbers, like million. What's a negative million squared over a million plus 1? See what happens. Then try a trillion. And you'll probably see it keeps getting very, very large in terms of negative numbers. So always keep that in the back of your mind too. All these tools we can use to find a limit. All right, here you go. So what we're really concentrating on right now is you and I are like, hey, let's hit these things graphically. But even better, you're like, if it's a rational function, won't it just be the Horace? try to find this one. X minus 6, x squared, minus 3x, plus 11. The limit as x approaches infinity. 3x squared minus 5 over 2x squared plus 1. Usually I say, show all work for full credit. Right here I'm just like, you can just find the limits. Here's another one. Find the limit as x approaches infinity of x cubed minus 9 over negative 4x squared plus 5x plus 1. All right, they're all limits to infinity. This topic, limits at infinity. Let's one at infinity. You could go and make the entire graph if you wanted to. On this one, highest powers in the numerator, you could go find the slant asymptote if you wanted to. But please feel free to use these tactics, these easy tools. In these two scenarios, it's going to be the horizontal asymptote, right? True? Just find the horash, you'll get the answer. This one has a slant as, so we're going to look at the end behavior, right? Joe, do you know this one? Where's the highest exponent?
On the bottom.
On the bottom. And when the highest exponent's on the bottom, no matter what, where was the horace every time in a rational function?
0.
Always 0. It's always 0. So guess what this is going to be?
0.
By the way, I'll show this other ways we do these problems. There are numerous ways to find these limits. There are. But this is just one easy way. You're like, it's a rational function. I know what the horizontal asymptote is. That's going to be the answer. This graph is going to head towards the horizontal asymptote. How do I know it's 0, everyone? 3x. There's no x here, there's no x here. I look for the highest exponents. There was a 1 versus a 2, higher exponent at the bottom. Now here the exponents are matching. Highest exponents in each part are matching. Where's the horace in that scenario?
3 halves.
3 halves, good job. Or if you want to write 1.5, that'll work too. I'm doing this without any graphs, because of our knowledge, this works. Yeah, yeah. So you can just do that, of course you can. I think it's great, that you're just applying it, you understand where the horizontal asymptotes are. Don't need to make the graphs, you're just asking for the limit. All right, do you remember a fast way to do this, where you don't have to make the graph and get the slant asymptote? I want you to think of the end behavior if you simplify it. Let me hide that 9, I'm going to hide that 5x, hide that 1. Does anybody know the end behavior of that graph? It would be a negative 1/4 x. So what's the end behavior of y equal to negative 1/4 x? That's a straight line. Which way is it going? It's going down. So what's the answer to this limit? Positive infinity or negative infinity? I do want to point out, this is either going to be an infinity or negative infinity. If you really wanted to guess on a test, it's a 50-50 chance. This will always be infinity or negative infinity, but no. Let's look at the end behavior. It's going to negative infinity, isn't it? That's what it is. So we get negative infinity. That's what you get because that 4 had a negative in front of it for the coefficient.
I have a question. How do you find the limits of the first one and the second one?
Oh, how we found these? We knew that these would be the answer because we knew these were the horizontal asymptotes. Remember we made the graph earlier and the highest exponent was on the bottom? The horizontal asymptote will always be, I'm just going to draw, not the entire graph, but just, I'm going to show you where this horizontal asymptote, it's right here. And so what will the graph do? Whether it's up here or down here, it's going to bend and curve towards that. Now in this scenario, these powers are matching. That's your horizontal asymptote. So this graph's going to do what at You know, there's 1, there's 2, 3 has to be right in the middle, 1.5. This graph is just gonna bend towards that. It's gonna approach this. If it's up on top or it's down on the bottom, it's still gonna approach it. And in fact, actually it will approach on that side too. So that's what we're doing, and feel free to do that. Was that okay with all these? Now, I really should show you something. I get a lot of students, let's say they're taking my Calculus Online course. I don't see this. I see a lot of algebraic work. Maybe they get it right, maybe they get it wrong. I get all these steps, so I want to show you what they've been taught. And it works. Like what would a solution manual say? I just want to show that to you, okay? What would a solution manual show for this? Can I erase these two? Yeah. So I want to show you this too. This is what a solution manual. So send me, I get students who go, oh, I like that better. They don't like graphing and shortcuts, you know? They're like, oh, I'll just do this. All right. Gets us out of the way, we're looking for this limit. All right. So, when I want you to look at all these expressions in here, that's an x, that's a 6x to the 0. That's x squared, that's a 3x, that's 11. Of all those little monomials in there, what's the highest power you got? X squared? So what I'm going to do is, do you agree in math, that beating math, you can multiply 1 to anything? So what I'm going to do is, I'm going to go up to this expression, I'm going to multiply 1 over x squared over 1 over x squared. Okay? So I'm in this top, this numerator, I'm going to multiply 1 over x squared, and then in the denominator, I'm going to multiply 1 over x squared. Right? So this is what a solution manual would show. Now, my next step, let's see what we get. No, you don't have to do it this way. What's 1 over x squared times x? 1 over x, very good. Minus 6 over x squared. X squared times over an x squared is just the number what? 1 minus 3 over what? X, and what's that last part? Plus 11 over x squared, right? So far so good? Now this is going to be helpful to us. What's the limit of like a 1 over x going to be? Just going to be what? 0. And we're going to use that to our advantage. By the limit laws, this would be the next step in the solution manual. They'd show this, they'd show this. Now, the limit law says you can write this limit next to that, 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 and just find all the limits and see what you get. So I'm going to do that, okay? It's going to be a lot of writing. So I mean, so watch. I'm going to write lim, x goes to infinity of the 1 over x. Minus, the limit is x goes to infinity of the 6 over x squared. Some of you might be already tired, like, we know the answer, it's just 0. I'm going to give you a limit as x goes to infinity of a 1 minus the limit is x goes to infinity. This is no lie. This is what the solution manual would show. Plus the limit is x goes to infinity of the 11 over the what? X squared. But I see this all the time. I've been taught that in high school. It works, they like it, and they just keep doing all this, and it's no problem. Now you gotta find all these limits. Well, what's that limit? 0. What's that limit? Do it numerically. 0. You probably already know the answer because you're getting zeros on top. That's a 1. And when you agree the limit x goes to infinity of a 1 is just 1, it stays flat line 1. No matter what, it's always 1. Okay, so that's 1. What's that limit? 0. What's that limit? 0. You agree? Well, what's that mathematical answer? 0. So I want to point that out. That's another way to do these. You look for the highest. I looked for the highest power I saw, and I did a 1 over that in the numerator and denominator. It works. Just takes a lot, but I see that all the time. You might, that's a lot of writing. Some students don't mind. They just go and they just keep writing it out. But I have seen them all write it out like 8 steps like this, and they get it wrong. They mess up just one of these. What happens? Yeah. Out of 1, 2, 3, 4, 5, mess up just 1. That's all it takes to throw the thing off. True. Like if they didn't see that was a 1, they put a 0 there, and I might go 0 over 0. And then think does not exist. What do you think about that? Excellent, excellent.
You said you took the x with the highest power.
Yep, and then I did 1 over that. So if I saw like, no lie, if I saw like an x to the 5th up in here, and an x to the 6th down here, and then all these other powers that were lower, I would have done a 1 over x to the 6th over a 1 over x to the 6th.
But it's still be 0.
And you'll still get to be 0.
I-
Yeah, you're right.
No clue how you got that, but I'll do it.
Yeah, you like it. Hey, that other one, I'm gonna rewrite the one I had. What was the second one I had where the powers were the same? It came out to 3 halves. What was it? 3x squared, 2x squared. Do you remember what I had there?
-5 and plus or minus.
Oh, thanks. So, what's the highest power you see?
2.
If he likes it. Okay, so you would multiply up here a 1 over x squared, and then the denominator you'd multiply a what? 1 over x squared. You distribute it, you would distribute it, and do all the math, but you should get, if you want to try it, you should get the answer of 3 over 2.
So you ignore the coefficient is numbers.
That's right. Isn't that cool? That's what you're looking at. You're ignoring the coefficient. Because the beauty of math is, I'm allowed to do this, aren't I? I'm multiplying the expression 1 with the number 1. 1 over x squared over 1 over x squared is 1. Did you want me to finish that one out for you?
No, it makes sense.
Okay, he's got it. So some students like that. Like, oh, I don't like the graphs. I don't like whoreasses. You know? I like this. This is all out. They're algebraic. They're algebraic thinkers. They like the way that it works. That works even with the x cubes and stuff. Cool. All right, so are there any weird, bizarre ones? Yeah. What if it's not rational, but it's a fraction? So in this phrase I was just saying, rational, like this number in math is rational. This number is not rational. So what if it's a fraction, but it's not a rational expression? Well, I guess that game's over, huh? Well, we can still use parts of it. So I'm going to give you an example. What if you got something that's not rational and we still want to use some techniques here? Well, you can do it the way we're just doing. You can still do it. But here you go. How about